Okay, great. Hi, everyone. So can you all see the slides that I'm sharing right now? Yes.
We can, yep.
All right, so basically, this module was created by three of us, and we're sort of spread out throughout the US. So I'm at California, at Humboldt State, Shangping is in Wisconsin, and Hugo is in Texas. So we all kind of had different areas that we were interested in creating some authentic learning activities for the DLC. So generally for this module, we're all coming from different sort of teaching loads. So I mainly teach undergraduate engineering students. And so I was really interested in creating a module that would fit into a 1-week period for my introduction to hydrology course. And Hugo and Chengping had more advanced graduate students. So we kind of made a mix of learning activities. And we've set this module up so that people can kind of pick and choose between the subsections and the activities. Maybe it might make sense to split it up into two modules at some point, but we're starting out with one with all of these different components. So the topics that we wanted to cover are these 7 listed here. So basically just a general global overview of evapotranspiration, thinking about its context and its importance in the global water cycle. Then using the water budget method for estimating ET from a clearly defined system like a lake or a watershed, and we have a learning activity associated with that. Then we have a section on how do we measure ET. We have a section on what parameters related to ET. Particularly, we're focusing on our calculation of reference evapotranspiration there. So basically all of the input variables for the Penman-Monteith equation, which is sort of our culminating activity. Then we talk about PET estimation, so potential evapotranspiration estimation, and these we're focusing on the simpler methods like temperature-based or temperature and radiation-based methods. Then we gave Penman-Monteith its own section in our module because it's considered the standard for the best estimate for evapotranspiration. And then we have a module that is sort of our culminating capstone activity that is looking at differentiating between evapotranspiration and transpiration and irrigation management using remote sensing. So it's got a lot of components in it. So in addition to all of the learning objectives that we would associate with those topics, we also sort of brainstormed and thought about what are some additional objectives that are important for our students to get. And so we also wanted to talk about, do students understand how to select the methodology? There's so many methodologies out there for estimating evapotranspiration. Can they predict what should happen seasonally and in different climate scenarios? We also do focus a little bit on how students are communicating their results, presenting their graphs and their results with appropriate significant figures. And we'll probably talk a little bit more about those other learning objectives when we talk about the activities. So we have 3 main resources or data sources for our learning activities. We have like I mentioned, we have a water budget activity that's using data from NOAA to look at estimating monthly trends, and that's using Excel-based calculations. Then we also rely quite a lot on the eddy covariance data sets that are available in the Ameriflux network. So these are, high resolution, temporarily high resolution measurements of evaporation and energy fluxes at one point location. So it actually gives us an opportunity to compare our estimates with actual measured values, which isn't usually the case when we're estimating ET. And then that activity is actually based in the programming language R, And so we use the quasi-Jupyter Hydro Share platform for that. And then finally, we are also using Landsat and Sentinel data sets for our final management learning activity. So I'll just briefly talk about the Ameriflux activity and then pass it on to Shangping. So the learning activity that I put together that was based it when we're talking about parameters that are important related to evapotranspiration, it is an activity that's based in R, as I mentioned, but we really didn't want to limit this to students who were experienced programming in R. So it's set up in a Jupyter Hub account where most of the coding is already done for students. We're basically trying to get the students to focus on how do they extract useful information from the data source, so from the Ameriflux website. How do they figure out where their parameters of interest are within the data set? How do they interpret the metadata? And what are the different site characteristics and how does that play into what they would expect to see seasonally here? So this is kind of an example of a plot that is created automatically for students. So they don't need to, all they need to do is kind of click run on each of the chunks and they can create this plot. So basically we're trying to get them to focus on how do you interpret this. So they're able to then look at, here are three different, very different sites from this FluxNet data set. Site 2, this is the red dotted site here, is a wetland site. So it's not water limited. It's going to have plenty of water available for evapotranspiration when that occurs. Site 3 is an evergreen site, and that's very high altitude. So it's going to have limited growth early in the spring. And then site 4 is a savanna, very water limited site. And so we can see what we want the students to be able to interpret from these types of graphs is why are the patterns different in these three sites? What information can they gather from the websites, background information to be able to interpret that? I think that's all I wanted to cover from my slides. So I'll just hand it over now to Shangping and Hugo to talk about their sections. Oh, Shangping, you're still muted.
Okay, I will move next, and then I think Hugo will continue, and I will be. So basically, let me see. Sure. So I will switch between the HydroLearn site and some of the files that we want to use. This was the Lake Michigan Huron data that we want the students to do some calculations from the beginning of the month, the water level, precipitation, you have the inflows, outflows, and you have runoff inputs, the diversion, and then the students will need to do the unit conversion. We have practices for the student to do. You have, cubic feet per second into millimeter for the lake and things like that. They will be able to do that, and then they will look at the water balance and then calculate the ET and look at the patterns of the ET. Actually, this one is a very interesting one because the ET pattern is very different from what they would expect. So let me see. I want to share another one. I'll stop share with this one. So interesting. I have a Firefox. It doesn't allow me to. Oh, here, yes. This was the water budget. You know, we have the water budget and the background and things like that. We have the Lake Michigan one, just because, oops, it logged me out very quickly. You can see the importance of looking at this ET, because you can link it to erosion, link it to damage to infrastructure and those kind of things. So that's the water budget one. And then I will talk briefly about, say we talk about the measurement of the PET and ET. We talk about the pan evaporation. You know, we follow kind of the FAO, you know, we show the instruments, the design of it. Some estimations for just to have a kind of general idea of the pan evaporation in the US and the coefficients, if you want to use it, how can you estimate to, from the pan evaporation, how to estimate the kind of the reference ET or the potential evapotranspiration. And then the center will do some example calculations using some of these equations. These are the Food and Agriculture Organization kind of version of it prepared by Alan and others. We talk about the lysameter method. We have some videos. I think here's some illustration. How do you do the calculation? Very simple. And then there's some videos that can really show how these kind of lysameters work to measure the evapotranspiration. We have some practice calculations for the student to do it. We have the kind of added covariance, you know, as Joe just showed that, you know, we have the data sets, here's the theory basis for that, you know, just the basic theory for that. And then we look at the PET estimation method. As Joe mentioned, we have the temperature-based, which is very simple, like the banana cradle. You know, this is a very pretty much it's a temperature-based method. You can do some calculations. We have some, you know, kind of radiation-based. But we pick these ones because this method, you can have tons of different methods. So we pick these ones mainly because these are the ones that were used by some of the popular hydrological models like HAC HMS. They use Taylor, they use Pimment-Monteith, they use Hargreaves and Harmon. So we talk about these models. We talk about the models and, you know, and give them some practice questions to do that. And if you look at more on the groundwater side, we have GS flow. This is from USGS. You know, you can see that it's the Jensen Hayes, you have Harmon, you have the pan evaporation. This was the PRIMS. This is a runoff or groundwater recharge model, but it has this evapotranspiration component. You have Harmon, you have Jason Hayes, you have the Hargreaves, Percy Taylor, and the Pimment-Monteith. So we pick these models because they are kind of incorporated into this kind of widely used hydrological modeling programs. And so we, so we talk about these models. We ask the team to do some practice questions and things like that. I think maybe 7, 8 plus Pimment-Monteith. So that's the estimation method. And then I think I turn over to Hugo, talk about Pimment-Monteith and talk about the water management from the perspective of evapotranspiration water need.
Thanks, Changping. Now let me share my screen and okay, I will talk about this. The idea of the last sections of the module is to let me see if can you guys see my screen? Yes, there you go. So this is as you can see, the model has different sections. It's very comprehensive because it covers a wide array of the different methods that you could use calculate or estimate evapotranspiration. And we wanted to have a final couple of activities that were like a capstone sections where the students would have an opportunity to use the knowledge they gained through the earlier sections and use it in a context of real, life application also in a very interactive way. So for that, we did basically two things. And I'm gonna show you the examples. Let me see if I can do that here. We have a learning activity that includes calculating transpiration from remote sensing imagery, basically using Sentinel data, where we give the students an opportunity to do a little bit of coding. Although they are not required to be experts, in programming, it would be good to have some notions. So this is more geared towards senior undergraduates and graduate level students. And basically, we give them a nice introduction into some of the tools that we will be using, which is mainly two: Google Earth Engine to process the remote sensing data, and the Google Code Laboratory to do some calculations using Python. So in this learning activity, we have very detailed instructions and videos on introducing these technologies or these tools. And then we have small pieces, small chunks of code with very detailed explanations so that the students are not given the entire code, but rather, they are explained all the different parts of the code and what it does, so that they can copy and paste into their own code editors, both in Google Earth Engine and in Python in the Google Code Laboratory. So as you can see, this is a long learning activity, but we think it's very interactive. This is an example of the Google Earth Engine editor and the script that they will be at the end coming up with after following all of those directions. And if we run it, we will see that we will be actually getting the data sets, different kinds of data sets, and even some products where they will be able to see, how the evapotranspiration or the vegetation indices change over a crop area. And so they will be using all of this information that they gather to then process it in Google Code Laboratory, again, producing a script that is going to look something like this, and which at the end, it will show them, the final reference of evapotranspiration from a real place with real data, and the breaking in of the evapotranspiration into transpiration for the crop parcel at the end. And so once they're able to work on this learning activity, they will be now ready to take on the last one, which is an authentic real life example of an application of these methods, where they get exposed to an area that has, issues with an aquifer that is being overexploited by using this water to irrigate crops in an area that has a little precipitation, and where the way that farmers are using the water actually does have an impact on the water resources of this place. So they're given all of the background information, including the site where they will be asked to work on two different parcels, having two different irrigation systems. These are the parcels that are delineated here in yellow, and using all of the information and the knowledge they gain on using Google Earth Engine and using the notebooks in Google Code Laboratory, they will be asked to come up with a series of analyses on different irrigation methods for these two different parcels and how that impacts, the water management and the water balance at the plot scale. And so this is, I think this is all we wanted to show you. We would like to know what you think about this. Thank you.